Good morning. In the last lecture, we found out how to get fixed end moments due to load on the member itself. Today what I'm going to do before I start off looking at problems, etc., I'm going to give you a few exercises which I would like you to try out on your own using the procedure that I developed in the last lecture. So what I'm going to do is, I'm going to give you a few this I've already done for you. This is PAB squared upon L squared. This is PA squared B upon L squared, where this is L. And of course uniform beam. Then I'll give you a few others. This one I've already done. So using exactly the same procedure, I would like you UDL W over length L, this is equal to W L squared upon 12. This also I have done for you. Do some of the more interesting ones. This is a linearly varying intensity of load, where W is the intensity at the end. Partial uniform loading over part of the, where this is A and this is B. Okay. Then we'll call this L minus A. This is equal to W A squared upon 12 6 minus 8A upon L plus 3A squared upon L squared, and this is WA cubed upon 12L 4 minus 3A by L. Satisfy yourself that if you put in A equal to L, then you're going to get this. Okay? So this is important, because if A is equal to L, then this you have to recover from this. And finally, I'll give you one more. Acting at a distance A and B. And then this is, sorry, this is this way, this is this way. This is equal to M upon L squared A into 2B minus A, and this is equal to M upon L squared B to A minus B. Satisfy yourself that if A is equal to B, then this has to be equal to M upon 4L squared, 4L. m upon 4. These two would be m upon 4. Okay, so I would like you to actually look at all these solutions that I have given you, and you should be able to establish the fixed end moments by using the method that you've already developed. Okay, so much for all of this. What does this do to the slope deflection equations? If you really look at it, what is the definition of fixed end moment? Let me first write down the entire equation. Okay, these are the complete equations. Look at this. If theta A B equal to 0, theta B is equal to 0, and delta equal to 0, that's the fixed case. Okay, what is MAB equal to? The fixed end moment. That's what it should be. Okay, similarly this. So this is the final equation, the final slope deflection equations, which actually present the member force displacement relation. Okay, essentially if you look at this is the member force displacement relations that you have. Okay, now this is the final equation that we are going to be using. Of course, we will see later that there are several things that come out of this which we have to use. But now we will start looking at problems and see how we can solve those problems to be able to get your solution for equation. Now let me give you one thing. What I want to give you is that you should be able to remember the problem that I had given you. Remember this problem? Try solving this problem defining degrees of freedom. Okay? Right now, how many degrees of freedom would this have? Well, if you look at it, 1, 2, 3, 3 degrees of freedom, and you can set up 3 equations, etc. I leave it up to you. You can solve this. Let me solve some other problems, and I'll come back, I'll revisit this problem in a different light. I'll talk about it a little bit later. Okay? Let me now look at some standard problems that we can solve. Okay, and the loading here, this is 10 meters, this loading is 4 meters, and this load is 120 kilonewton, and I have loading here, this is 50 kilonewton per meter. Okay, and you are given the fact that this is EIS is the same. Uniform beam, multi-span uniform beam. Okay, continuous over two supports. Okay. So let us now do this, and I'll write this as A, call this B, and I'll call this C. EI is a constant. Okay. So let us look at this particular problem. Okay. Now, how many degrees of freedom? Well, let's look at it. 1, 2, 3. So 3 joints into 3, 9. How many restraints? So these are the unrestrained degrees of freedom. Restraints are 3 here because it's fully fixed, 1 here and 1 here. So that is 5. Okay. And then we have constraints. What are the constraints? Constraints is that both the members are actually rigid. If they are actually rigid, then 1 into 2, 1 constraint per member. There are 2 members, so 2. So these 2. So total degrees of freedom are 2. What are they? Those are the rotation here and the rotation here. So let me look at what is the possible kind of situation that you're likely to have. Okay. If you look at this, okay, we'll have something like or maybe, where this is what? This, by definition, is theta b. And this is actually, the way I have shown it, is minus theta c because it's clockwise. Okay? So, or I can define it in this fashion. Let me actually do it in that way. That will make it easier for us to understand. So I'll draw this and then do this, so that by definition this is theta c. So that means what we have are, we have 2 unknowns. Look here, the theta a is equal to 0. Theta b we don't know, theta c we don't know. So what we don't know are theta b and theta c. But for the member boundary conditions, we know theta. So member boundary conditions, theta AB is equal to 0 and theta BA is equal to theta B. Theta BC is equal to theta B and theta CB is equal to theta C. What is delta BA? Since there is no deflection, delta CB 0. Always note that the delta is of the right end relative to the left end. So that's why it's always done in this fashion. Okay? So these are our boundary conditions and compatibility conditions. Okay? Where the unknown displacements are these. So therefore, the overall thing is that we have to use the slope deflection equations to be able to find these values, and once we find these values, if we find these two, remember that we can find these, and then we can find out the member end moments, and that becomes a statically determinate structure. Okay? So now let's look at how to solve the problem. Now again, the whole point here is that once we've written these compatibility equations, we write the slope deflection equations for each member. Okay? So what would be the slope deflection equations? Okay, the slope deflection equations would be MAB is equal to, if you look at it, 4 EI by L, right? So it is going to be 4 EI by L theta AB plus 2 EI by L theta BA minus 6 EI by L squared delta BA plus the fixed end moment due to any load on the member AB. Okay. So if I substitute the values of theta AB and theta BA that I have written down here, if we look at this, this is my theta AB, theta BA and delta BA. If I substitute those in, what do I get? I get 2 EI by L theta B plus fixed end moment at AB. Similarly, I can get, and I'm not going to write down this equation, I can write down the same equation, but if we put it in, we will get 4 EI upon L theta B plus fixed end moment at. Okay. So now, so you see MAB and MBA are in terms of theta B. Okay. Now these fixed end moments I'll find out a little bit later. Let me write down equations for MBC. Okay, again MBC, by writing down the equations of motion, slope deflection equations, and substituting that theta BC is equal to theta B and theta CB is equal to theta C and delta CB is equal to 0, what I get is the following: 4 EI upon L theta B plus theta C plus fixed end moment at BC. And similarly, MCB is equal to 2 EI by L theta B plus 4 EI by L theta C plus fixed end moment at CB. Now we need to find out, we've got these equations, but we need to find out what these are for the given loadings. Okay. So if you look at it, what is the loading on AB? Note that if there is no loading on member loading on AB, then these will be automatically 0. Okay. But let's see what are the loads on the member. The load on the member is, member AB has a load here which is equal to 120 kilonewton. Okay. So this is A and this is B, and I need to find out this is at 4 meters where this is 10 meters. So I need to find out these fixed end moments. So if I look at it by plugging it in to the formulae that we've already developed, note that my definition of fixed end moment positive is if it's anti-clockwise. So if you see, this is going to be this way, this is going to be this way. So this FEM AB is positive, it's plus 120 into 4 into 6 squared upon L squared. So what is that equal to? That is equal to 172.8 kilonewton meter. What about fixed end moment at BA? If we look at fixed end moment at BA, this is plus, that's going to be negative. So it's going to be negative 120 into 4 squared into 6 upon 10 squared. So this is going to be equal to minus 115.2 kilonewton meter. So these are the fixed end moments at AB and BA in member AB due to this 120. Similarly, I can find out on member BC, what is the loading? The loading is 50 kilonewton per meter. This is 10 meter. So these are going to be these way. So my fixed end moment at BC is equal to plus W L squared by 12, which is equal to plus 416 kilonewton meter, and fixed end moment at CB is equal to minus 50 into 10 squared. Minus because I am assuming anti-clockwise to be positive. Please note that. That is my sign convention, that I assume anti-clockwise to be positive. Others may choose clockwise as positive. Okay? There are various ways of solving this problem, but understand that as long as you use one particular method, then those you have to be consistent. You cannot keep changing your values. So this is my fixed end moment AB. This is my fixed end moment at BA. This is my fixed end moment at BC. And this is my fixed end moment at CB. So let me plug those in to my equations, and what do I get? I get that MBA is equal to 4 EI, and now I'm going to put in the value of 10. So it's 4 EI upon 10 theta B minus 1152. MAB is equal to 2 EI upon 10 theta B plus 172.8. MBC is equal to 4 EI by 10 theta B plus 2 EI by 10 theta C plus 416.7, and MCB is equal to 2 EI by 10 theta B plus 4 EI by 10 theta C minus 416.7. So these are my member end moments. Now let me look at, so what do I have to now do? I actually have to write down equilibrium equations, which two equilibrium equations, so that I can solve for theta B and theta C. Let's see what those equilibrium equations are. So let us look at the equilibrium conditions here. Okay, now let's look at it. Okay, at joint A, you do not have an equilibrium. The equilibrium says that MAB is equal to the moment at A. That does not give you anything. Let's look at joint B. At joint B, what do we have? From AB, we have MBA. Then we have the joint, and then from CB we have MBC. So if I look at the joint itself, what do I have? MAB and MBC, and then if I take the moment equilibrium at the joint, what do I get? I get MBA plus MBC is equal to 0. Similarly, if I look at joint C tells me what? MCB this is MCB, and if I look at it, by definition, since the moment is 0, MCB is equal to 0. These are my two equilibrium equations. Now I substitute MBA and MBC that I have written down earlier, and if I put those in by substituting these that I evaluated into these equations, what I get is 8 EI upon 10 theta B plus 2 EI by 10 theta C is equal to 301.5. Okay, and the other equation is 2 EI upon 10 theta B plus 4 EI upon 10 theta C is equal to 416.6. So I have two equations in theta B and theta C, and I can write this, I can actually solve this. Well, the easiest way to solve this is by writing it in matrix form and solving it. So I'm going to put 2 EI upon 10 outside. So inside what I have is 4, 1, 1, 2 into theta B, theta C is equal to 301, 416. Okay, so then what do I get? If I solve for this, I get theta B equal to, theta B is equal to 728 upon EI radians. Theta C is equal to minus 1406 EI radian. Okay? I have solved for theta B and theta C, and I can actually draw the deflected shape now. Okay, because if you really look at the deflected shape which we had drawn earlier, okay, look, now I know what theta B is and I know what theta C is. If you looked at it, theta C is, that means essentially what this means is that if you look at it, that this goes, the deflected, actual deflected shape goes in this fashion. Where this is negative and this is positive. Okay? So that's negative and that's positive. But anyway, that does not really matter for me. What was my interest? My interest was bending moment diagram. So now when I have these and I put that into the equation that I have here. See, now I know theta B and theta C, so I can put those in and I get my MAB my MAB is equal to 27.2 kilonewton. MBA is equal to minus 406 kilonewton meter. MBC is equal to plus 406 kilonewton meter, and MCB, if you look at it, is going to be equal to 0. Okay. So if I look at this, then what am I getting? I am getting the following. Let me now draw. I'm going to break what have I broken these up? This is my moment, the moment at the fixed end. Okay. Now, if you look at this, that this is equal, this will, to balance this, I need something like this, and to balance this, I need MAB. Then, so this MAB is equal to 27.2 kilonewton meter. Then I have this load, 120 kilonewton. Then I have minus 406. What does minus 406 mean? Minus 406 means that it is clockwise. So clockwise and this way. Okay. Then I have this will be going this way, and what is this value? This is 406. And note, at BC also I have 406 anti-clockwise. So this is correct. It goes this way. And then on this side, what do we have? 0. 0. We have this, and over we have this. Okay, so these are my member end moments that I have obtained over there. I have put them in here. Okay, now I need to find out the shear forces also. Okay, so if you really look at it, how do you evaluate that? Take member AB. Member AB at this end has 27.2. I'm just writing down the values now. Huh? I'm not writing down the dimensions, because we already know what the dimensions are. In addition to that, at 4 meters you have 120. So if you look at this, to find out the shear force at AB, okay, the shear force at A. If we say shear force at A, how do I obtain that? Well, to find out the shear force, I can take moments about this end, because you see over here I have shear force over here too. Okay, so if I look at it, what would this shear force be equal to? Let's look at this. Okay, take moments about this end. What you will have is VA into 10. Okay, so you have VA into 10. That's clockwise. Okay, then this is anti-clockwise, so minus 27.2. Okay, then this is clockwise, so it's plus 406, and then this is anti-clockwise, this is minus 120 into 6 is equal to 0. So this gives me that the shear force is equal to, if you look at this, 720, so it's going to be 72, and then minus this is going to give you 379.3. So I'll just put that in. So divided by 10, so it's going to give you minus 37.9. I'm dropping the 3, of course. And so VA is going to be equal to 34.1 kilonewton. Okay, let me look at this one here. Obviously, this one, the shear at B, VB is going to be 120 minus 34.1, and so that is equal to 85.9 kilonewton meter. Okay, so this is the shear at A, and similarly for this, with the loading of 50 kilonewton meter, you will see that V at C turns out to be equal to 290.7 kilonewton, and V at D turns out to be equal to 209.3 kilonewton. That essentially comes from 40.65, 406.5 divided by 10 plus 250. Okay, so one place you have additional, and in one case you have less. Okay, so these are our shears. So now let us draw the bending moment diagram. How would the bending moment diagram look? The bending moment diagram would look in this fashion. Let's draw the shear force diagram first. The shear force diagram is a simple one. Okay, if I look at it, and again I'm going to draw it in one direction and be consistent. Okay, so I'm going to drawing it in this direction. What is the value? 34.1. And what is the direction? If you look at this direction, it is this way up, this way down. Okay, then that's a constant till we hit 4 meters. 4 meters, it goes to minus 85.9. Now this minus is all doesn't matter. Plus minus is really irrelevant for us. Okay, so this is going to be this way. In reality, I always consider this as positive, but it doesn't matter. I'm just drawing it. Okay, then what do we have? Then if you look at it, it has to go to 290.7 on the other side. So here it's going to go up. This is going to be 290.7, and from there, because it is linear, this is going to be 209.3, and because it's UDL, it's going to go like this. Okay, so this is going to be this way, and this is going to be this way. This is my now what is the reaction at B? Reaction at B is going to be 290 plus 85, if you really look at it, and that's going to be equal to 376.6. That is the reaction, upward reaction at B. What is the reaction at C? The reaction at C is going to be 209.3. Okay, so that's my shear force diagram, and let's look at our bending moment diagram. Bending moment diagram is going to be equal to, look at it, this is going to be 27.2. Okay, then it's going to go down because this is constant. It's going to go down to this value. This value is going to be equal to 109.5, all kilonewton meter. Then from there it's going to go up at this point to 406.5. That is the bending moment at B, and note that it is, so if you look at this, this goes this way and this goes this way. Okay, and then ultimately, if you really look at this, this goes this way and then 0 at this point where you have, this turns out to be 438 kilonewton meter. So this is your M diagram. This is again this way. Okay, so this is your bending moment diagram and shear force diagram, and that is the total analysis of this particular problem. Okay, so if you look at it, that this in essence gives you what the displacement method is. The displacement method, what did we first do? We first identified the degrees of freedom. Once we had the degrees of freedom, what was our next step? Next step was to evaluate the fixed end moments in each member, and the fixed end moments will only exist if there is a load on the member. If there is no load on the member, then it does not exist. Okay, so we find out the fixed end moments. Okay, and now I have already told you that you should be able to find out the fixed end moments given any loading from first principles. That's what I did in my last lecture. So you should be finding out the fixed end moments. Then once you know your fixed end moments, you write down the member force displacement relationship, which is given by the slope deflection equations. Substitute everything in. Next, write down the equilibrium conditions. Okay, the number of equilibrium conditions will always be equal to the number of degrees of freedom that you have. So essentially then the equations are in terms of the unknown displacements, or in this particular case for the beam, they are the rotations. Okay, so you find the rotations out by solving those equations, and once you find out the rotations or the displacements, then what do you do next? You substitute back into the member force displacement relationships, which is the slope deflection equations. Now you can find out the member end moments, and once you know the member end moments, then you can now take each member and find out its reactions, its shear force, bending moment, everything, and then you put it all together, and this is what you have. So therefore, given, I'm just going back to the original problem. Yes, this is the original problem. So given this loading on this multi-span beam, we use the displacement method to generate the shear force and bending moment diagram. Okay, so now to take it forward, let us look at another aspect of this particular problem, and that is that what do we do when we have support settlement. Remember that I talked about support settlement when we were looking at the force method. So let me take this particular problem itself, the same problem. (10 meters, 10 meters), no loading on the structure. Okay? But remember, I said that no loading on the structure. Why? Because we can always consider the loading to be done separately. Okay? And we can then consider other conditions. Remember that principle of superposition is valid always in all the problems that we do, because we are only considering linear elastic structures. And when you have linear elastic structures, you always can superpose. So let us just say that the loading that we considered in the previous case, due to that, this support settles. Okay? And what we want to do is, we want to find out what, we've already found out what the effect the load has. Now we want to find out what effect that this settlement has. And let's just assume a particular value, that it goes down by 30 millimeters or 0.03 millimeter. Okay? Then what do we have? If you look at it, this is going to become something like this. Okay? So again, I have theta B unknown, theta C unknown. Now, only thing is, since there is no loading, fixed end moments are all zero. They are all zero because there is no loading. Okay? So now, just quickly, you can go back to my equations. I am just writing down one of them. MAB is going to be equal to, substitute these values in, and we have the same compatibility conditions. So this becomes 2EIL by theta B. Okay. Now, do we have a delta BA? Note that we do have a delta BA. This is gone down relative to this. Now, I had always said delta BA is positive going up. So when it's going down, what is it? It's negative. So here you have delta BA as negative 0.03 meters. And what about delta CB? See, if you look at delta CB, B has gone down relative to C. So that means C has gone up relative. So it's positive, plus 0.03 meters. So if I substitute this in, this becomes plus 6EI upon L squared multiplied by 0.03 meters. Okay? So this is the way that you have to solve. Now what I will do is, I am going to spend the next lecture looking at how you can solve this particular problem in more detail. Okay? Now let us just put down some values, because you see, I will require the values of E and I to be able to get estimates on everything that we have here. So I am going to put down some values of E. E is 200 gigapascals and I is equal to 2000 into 10 to the power of minus. These are some of the values that you have been given. So then once you know E and I, you'll be able to solve for this. More about this when I go into my next lecture. So just to review, what is the procedure for the displacement method? Displacement method. 1. Determine number of degrees of freedom and identify them. 2. Determine fixed end moment if loads on members exist. Write slope deflection equations for each member. 4. Write equilibrium conditions for structure. Solve equations for unknown displacements. 6. Substitute known displacements into slope deflection equations so that you can get your member end forces, member end moments, and once you get your member end moments, you should be able to solve. Okay, so I'm going to stop here, and the next lecture I'm going to take up on this particular problem and show you how to solve this problem for support settlement using the displacement method. Thank you very much.